So we're going to do a summary, a recap of what we did yesterday with natural logs. And then we're going to consider log base b of x, which is the general logarithm. And the big theme for today is that all logs, log base b of x, are essentially natural log of x times a conversion factor, or times a stretch factor. That's the point of today's lesson. So, to review from yesterday, the definition of natural log of x is the inverse of e to the x. And immediately from that definition, we have the two following complementary equations, which both show that e to the x and natural log cancel each other to give x back. And because the natural log of x is the inverse of e to the x, that means that all of the exponential properties can be inverted to give properties of logs. So we had a product rule for exponentials. E to the x times e to the y equals e to the x plus y. And so when I essentially take the log of both sides of that, what I get is that the natural log of a times b is the same as the natural log of a plus the natural log of b. This is the product rule for logs. The log of a product is the sum of logs. Likewise, because e to the x over e to the y is equal to e to the x minus 1, therefore, natural log of a over b equals natural log of a minus natural log of b. And this is the quotient rule for logs. And likewise, because e to the x to the m power is equal to e to the mx, it follows that the natural log of a to the m power equals m ln a. And this is the power rule for logs. And yesterday I walked through several examples of using these log properties to solve equations. And in my other class, one of my students said that logs frequently confuse him. And so I asked him to write down questions and bring those into class tomorrow. So tomorrow we are going to take maybe the first 10 minutes to look at any questions that you might have with regard to logs. Okay. In addition to the algebraic properties, we also took a look at the graph of natural log of x. And the graph of y equals ln x is derived entirely from the fact that that natural log x is the inverse of e to the x. So we started with the graph of y equals e to the x, which has a familiar shape, and it has three special points that we all know and love: 0, 1, 1, e, and the horizontal asymptote y equals 0, which is reflected in our limit. The limit as x goes to negative infinity of e to the x is equal to 0. The domain of e to the x is all reals. The range is all positives. So when I graph the inverse, all of these facts are still true, and now they are inverted. So instead of having the point 0, 1, I now have the point 1, 0. Instead of having the point 1, e, I now have the point e, 1. And instead of having a horizontal asymptote y equals 0, I now have a vertical asymptote x equals 0, reflected in the fact that the limit as x goes to 0, but from the right only, because our domain is positives only, of natural log x is negative infinity. The domain and range for e to the x are likewise inverted, so that the domain for log is positives, positive reals, and the range is all real numbers. And in particular, the two numeric facts that we see on the graph here are that the natural log of 1 is 0 and the natural log of e is 1. And we will be using these facts a lot during this course. Please don't get them confused. Notice there's two different ones there, easy to get them confused. Make sure you're clear. The reason that the natural log of 1 is 0 is because e to the 0 is 1. The reason that the natural log of e is 1 is because e to the 1 is 0. Okay? So that's the graphs. Then we took a look at the derivative of y equals ln x, and this is an important, one of the most famous derivative rules. To get that derivative, what I did was to appeal to the same process that we did with the inverse trig functions. First we undo the inverse, then we differentiate, then we rewrite in terms of x. So to undo my inverse, I begin with y equals ln x, seeking dy dx. I undo the inverse with its inverse, so that e to the y is equal to x. Take the derivative with respect to x. And on this side, outside, inside, the derivative of e to this flat is e to this flat times the derivative of the inside, which is dy dx. This is a perfectly good answer, but I want to rewrite it in terms of x, and I observe that e to the y is x, so that the derivative of the natural log of x is simply 1 over x. And yesterday we did a large number of examples of differentiation. I want to do just one today. So as an example, the derivative of the natural log of e to the x plus 1. I'm going to think outside, inside. Outside function is natural log, and therefore its derivative is 1 over flat times the derivative of the inside. And then I walk term at a time. The derivative of e to the x is e to the x. The derivative of 1 is, so I get my answer just like that. How are we doing so far? You guys that were here, you can look at this thing. Does this make sense?
I'm good with this, with comments like the last one.
The last one?
Not what we did, like that.
Here. Yeah, well, this is essentially our derivation of this derivative rule. And the derivation follows the same pattern that we did for the inverse trig functions. First, we had an inverse that we didn't really know what to do with, so we undid it. Then we did the differentiation with respect to x. And then we expressed that in terms of x. In other words, 1 over e to the y is a true answer, but it's not generally very helpful to us. If I replace e to the y with what it is, which is x, then I get a much more helpful derivative. Does that make sense?
So when you're doing derivative of e to the x, So because derivative of x is 1, so we just did it right. So we still need to find dy dx here.
Let's see here. In other words, the difference between, I think what you're asking is the difference between this and this. Yes, exactly. So chain rule is always in operation. However, dx is simply 1. So I simply get e to the x, whereas here, I get e to the y times dy dx, or 1. Better? Yep. Okay. Okay. Well, I want to spend the rest of our time now looking at log base b. Simple principle. The log base b of x is the inverse of b to the x. In other words, b to the x and log base b are functions that cancel each other out to give us x. What we can do from this fact is to take all of our exponential properties and invert them, just like we did previously. We can take the graph of b to the x and invert it so that we get a graph of log base dx of x. But what I would like to do is actually cut to the heart of the matter and argue this, that log base b is the inverse of b to the x, but also we might call this a change of base formula. Log base b of x is also the same as natural log of x, but divided by a stretch factor, natural log of b. And if we can understand that the log base b of x is the same as the natural log of x times a constant, then it will make intuitive sense to us that all the properties are the same, the graph is very similar, the stretch, and so on and so forth. Question? Oh, well, I'm about to prove it. So this is my claim here, that log base b of x is equal to natural log x over natural log b, and I'm about to prove this. What I'm going to do to prove this is I'm going to compute log base b of x in two different ways by solving the equation y equals x equals b to the y. I'm going to solve x equals b to the y or y in two different ways. The first way that I have of solving it is to simply take the log base b of both sides, because the log base b is the inverse of the exponential b to the y. Therefore, these cancel, and I get y. See, easy solution. Now, I'm going to come back and I'm going to solve the same equation in a different way using natural logs. I'm going to start with x equals b to the y, and I'm going to take the natural log of those sides. here's where I get to be clever. I'm going to use the power rule for logs and rewrite ln of b to the y as y times ln of b. See what I did there? And then I'm going to divide both sides by ln of b to get a second way to write y. Well, here's the deal. If y is equal to log base b of x, and y is also equal to ln x over ln b, what is the natural conclusion? Those two must be equal. That the log base b of x is simply the natural log of x divided by the natural log of the new base. And we call this the change of base element. And it's useful to us because it allows us to compute logs of any base on the calculators and also with regard to calculus. And it also helps us to understand that all log functions are really the same function, simply transformed by the CL method. Grab your calculators here and I'll show you how this would be used. So suppose I wish to calculate log base 2 of 18. The really recent TI calculators have a log base b button, but the old ones don't. And so the way in which we would compute log base 2 of 18 was to use the change of base formula and rewrite that as natural log of 18 divided by the natural log of the base 2. And when we actually carry out that computation on the calculator, the calculator takes a while to pull itself up. And natural log of 18 divided by natural log of 2. What did I forget? Closing parenthesis. There we go. I get 4.1699. Huh, that's interesting. How in the world would I check whether or not this answer is correct? How would I check if this answer is correct, that the log base 2 of 18 is 4.1699? Yeah. Into what? If the log base 2 of 18 is 4.1699, then what other statement should be true also? There we go. We can check it by taking our base as the base of the exponential and seeing whether or not this exponent actually gives us 18. Let's find out. 2 to the 4.1699. Da, 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 da. Yes, no? Close enough. 17.9997. Why is it off by a little bit? Because of my rounding right here. If I gave a couple of extra decimal places, 2 to the 4.169925, there you go. So we check out. Okay, so that's an example of use here. And we might call this a numerical example, or numerical use. If we turn over now to the graph of log base b of x. then we can think about that graph in two different ways. First of all, we can think about that graph in terms of the change of base formula. The log base b of x is the same as the natural log of x divided by the log of the base, which means that the graph of log base b of x should look just like the graph of natural log x, but stretched by a factor of 1 over ln b. In other words, if this is the graph of natural log x, I'm going to do green. Y equals ln x with the two special points 1 comma 0 and e comma 1. Then my graph for log base x should be the same graph but stretched so that each y coordinate is going to be multiplied by a factor of 1 over ln b. In other words, I should go through the point e 1 over ln b, and I'm going to go through the point 1, 0 again, because there aren't any scale factors, so they can use it. A second way that we can look at this, though, is to base the graph of log base b of x off of the graph of y equals b of x, because these two are inverses. And this graph, for b is bigger than 1, is an increasing graph that goes through 3 special points that we know and love. 0, comma 1, 1, comma b, with the horizontal asymptote y equals 0. And that should correspond now to 3 special points, 1, comma 0, this is a little different, 1, comma b. This is a point that was not obvious on our graph, right here. Excuse me, b, comma 1. I forgot to invert. My point is actually to invert here, whatever b happens to be. Just like that. And you can see that that's legit, because if I actually plug in b for x here, I get ln b over ln b, which should be 1. So we have these two complementary ways of looking at the graph of log base b of x, either as a transformation or stretch of natural log x, or as the inverse of b to dx. And those give us the same answers. Does that make sense to everybody? Likewise, the algebra should be the same. If I start with the 3 properties of natural log, and I divide through by natural log b, then I get the 3 properties of log base b. Just like so. Natural log of x over y. Natural log x minus natural log y. Just like so. So the algebraic properties that natural log has are the same as the algebraic properties that your log base b has. You look perplexed. Good? And then finally, the real payoff for today is the calculus. And that is that the derivative of log base b of x be the same as the derivative of ln x over ln b. And 1 over ln b is a constant, and therefore it comes to the outside. And we usually write that to avoid confusion as 1 over x ln b. So, just to summarize, and then I'll do a couple of examples here. The log base b of x is the inverse of b to the x. That's its fundamental definition. And then it has the property that it is exactly equal to natural log of x divided by the log of the new base. And so from that, all of the properties come out, especially the calculus property that the derivative of log base b of x is the derivative of this change of base expression right here, which is 1 over x ln b. So let's see how this works in real life here. Well, honestly, in real life, usually we'll use natural log of x as our base function to work with. But if I am dealing with logs in other bases, then, for example, what's the most common base other than e that is used in scientific work? 2 or 10, exactly, and 10 is the most common. Although 2 gets used a lot in computer science. So let's say that I am dealing with maybe pH or something like that. And so I end up with an expression like log base 10 of x squared plus 1. Well, okay, I'm going to think of this as exactly like the natural log function, but times 1 over ln 10. So that what I get is the derivative of the outside function, the derivative of the log function is 1 over splat times ln 10 times the derivative of the inside. And that's it. Let's take a look at one problem in the book. I'd like to consider this problem here. I'd like to consider page 178, number 27. No, before that, let's do number 26, so we can see some important things going on. What we have in number 26 is y equals log base 3 of 1 plus x ln 3. And they now want us to find dy dx. Okay. Tony, I see you already starting here. dy dx equals ddxo. And at this point, I'm going to pause the video. And if you're watching along at home, go ahead and work this out. And we'll come back in just a moment. Okay, we're back. So we're going to think in terms of outside and inside. And if we think in terms of the outside, the derivative of all log functions is going to be 1 over splat time, in the denominator times the log of the new base. Now, we need the derivative inside. And the derivative of the inside is going to be 0 plus 1 times ln3. Notice that the natural log of 3 is a constant, not a variable. So the derivative of x ln 3 is ln 3 times 1. And when this simplifies, we get a bonus. What bonus do we get? Yes, that's exactly right. We did not see that cancellation coming, but they set up a problem to make it happen. Okay? Now, the reason we love logs is that logs allow us to turn multiplication into addition, division into subtraction, and exponents into multiplication. This is why logs were invented in the first place by John Napier in the 17th century. So one of the most important skills that we're going to have is the ability to take a log expression and decompose it according to the log properties. So let's call this log property decomposition. Log property decomposition. And what I want to do to illustrate log property decomposition is to take the log of a complicated expression, such as the log base 2 of x squared times quantity x plus 1 divided by quantity x minus 1 cubed. And what I'd like to do now is to use the log properties to decompose it into additions and subtractions and multiplications. And to do that, I want to observe that this is an a, the log of an a divided by a b, so that I can rewrite this whole thing as log 2 of x squared times x plus 1 minus log 2 of x minus 1. And here I'm just applying the quotient rule for logs. And then I can take each one of these expressions and further decompose them. So this first term right here is the product of x squared and x plus 1. So I can rewrite that as the sum of the logs like so. And in the next term, I have the log of a power. And finally, I can apply the power rule to that very first term. Just like so. Now, why would I want to do this? Notice what I have accomplished. I've accomplished taking the log of a complicated product and quotient, and I've converted it into the sums of and differences of logs. Everybody see that? Why might I wish to do this? Well, here's one reason. It's a lot easier to take the derivative of this than it is that. So, for example, using this guy right here, if I wanted the derivative of the log base 2 of x squared times x plus 1 over x minus 1 quantity cubed. Doing this by use of the derivative rule for the log would be awful, because I would do 1 over this times the derivative of the inside, which would require quotient rule and product rule of the other. Or I could do a log property decomposition on it, and immediately write this as 2 log base 2 of x plus log base 2 x plus 1 minus 3 log base 2 of x minus 1. Notice how it's pretty automatic to walk through and do that log property decomposition. All of my terms in the numerator are positive signs, all my terms in the denominator are being subtracted. And then I can go term at a time and do the log properties, the log derivatives for each term. 2 times 1 over x ln 2 plus 1 over x plus 1 ln 2 times the derivative of the inside, which is 1, minus 3 times 1 over x minus 1 ln 2 times the derivative of the inside, which is 1 again. This is much, much preferable to taking the derivative from the original form. See what I mean? We're going to do a lot of this tomorrow. And we're going to find that it greatly simplifies finding derivatives of certain functions.